All right, so we're going to go over chemical equations, that is, writing out a chemical reaction in its equation form, right? So we need to review a couple things. First off, the signs of a chemical change. How do we know if a chemical change has occurred? There could be a temperature change. There could, right, it could be bubbling, which indicates that a gas has evolved. What's another thing that tells us whether a gas may have evolved? Sometimes it doesn't bubble. If a new odor is detected. Okay, if you have two things and they don't have a smell and we mix them together, suddenly there's a smell. You don't always get, okay, bubbling, but a new smell indicates something with new physical properties has formed. Okay, so if there's an odor change, that's also one, Nicholas. Okay, change in color. What else? Yeah, you could get a precipitate, a solid is formed, right? Something new is formed, and so you get something that's maybe not soluble. So you get a, what do we call that solid? Precipitates. Okay, so those are all good things. Okay, all signs that a chemical change has occurred. In a chemical change, can you reverse it? No. Not usually. Okay, not without an input like of vast amounts of energy or something like that. Okay, but for the most part, a chemical change occurs because there is a more stable form to be achieved. Okay, through that process. Right, so it's like if you set, like if you have a campfire, after the campfire is all done, all you have is a bunch of ash. Okay, you can't get the wood back after that. Okay, it's gone. It's turned into carbon dioxide. It's turned into, water vapor. Okay, and all that kind of stuff. All right, so we're going to look at the types of chemical reactions as well. We're only going to go over the 5 basic types. There are subtypes of those types, but we're only going to go over the 5 main types. Okay, we're going to look at how to identify each reaction type. They are all considerably different. Okay, they all have something unique about them that would make them easy to identify. And then we're going to learn how to properly write a chemical reaction. And there's a few things that are pretty important. This lesson here, guys, is why you have to be able to write chemical names and formulas. Okay? If you can't write the formula for a chemical compound, then you'll never get the reaction right. Okay, so it's really important that if that is something you're struggling with, that you come in and see me for help on that, because otherwise it's only going to get worse when we start talking about this stuff. Okay. All right, so big thing with a chemical reaction. In a chemical reaction, our final products are chemically different than the starting reactants. All right, so if we have a chemical reaction, right, it might look something like this. Let's just go with, sorry, that's hard to see. All right, so in this chemical reaction, I've got hydrogen chloride, which is an ionic compound, reacting with sodium hydroxide. Okay, we would call these the reactants. Okay, because they are the things that are reacting. Then we have an arrow, which indicates this is what I started with, and this is where the reaction is going. Okay, and on this side, we would have this and this. Okay, we would have water and sodium chloride. This would be our products. Okay, so a chemical reaction is always divided up into 2 sides. If you didn't write that down, you probably should. Okay, so what's on the left is our starting materials. We call those our reactants. Okay, what's on the right-hand side is what we are left with after the reaction. It's what's produced, so we call them the products. Okay, so all reactions are going to go that way. Not all reactions are going to have 2 reactants and 2 products. Okay, some reactions may have 1 reactant and 2 products. Okay, if something were to like break down, or something may have 2 reactants and only 1 product. Right? There's lots of different ways that a reaction can go. Okay, So in this reaction, okay, we see that some things have switched places, right? So this goes along with Dalton's atomic theory, right? He said that in a chemical reaction, okay, atoms can be separated, joined, or rearranged. Which has happened in this reaction? They've been rearranged. All right, nothing's really been separated here. Okay, although to rearrange them, I guess you could argue you have to separate them. All right, but hydrogen and chlorine are not together on this side. Okay, hydrogen ended up with hydroxide, which forms water. All right, I know probably you're used to seeing water written like this, but we also read it like that. Okay. And then obviously sodium, which was with hydroxide, is now over here with chlorine. Okay, so we've seen a rearrangement, okay, of what we had in there. Still all the same elements, right? And that was the other thing that Dalton said in his atomic theory, is that you can't make new elements in a chemical reaction, right? That was where alchemy was wrong. That's what they were trying to do. We didn't do that, okay? We got new substances, yes, okay? New substances with very different physical properties. But they're still made of the same elements we started with. There's hydrogen, okay? Here's chlorine, okay? Here's chlorine, sodium, hydroxide, and hydroxide. There's nothing new, okay? Well, I mean, it's gonna look new, but there's no new elements. Everybody okay with that? All right. Now, the signs here that we see of a chemical change are the result of, we go from having this stuff, which has certain chemical and physical properties. For example, hydrogen chloride is a strong acid. Sodium hydroxide is a strong base. Yeah, anything that has hydroxide in it is a base. Anything that has hydrogen acting as a metal, okay, is an acid. So this is an acid-base reaction. So on this side, I've got water, which is neutral, okay, and sodium chloride, which is also effectively neutral, right? So I go from having an acid and a base to having salt and water. Right, which is what you get every time you mix an acid and a base. Okay, when you mix an acid and a base, you end up with a salt, that is an ionic compound, dissolved in water, right, as the end result. Okay, so because those have different physical properties, we see this. It's not that the reaction causes this, it's just that we have something different on the other side that has different properties, right? Another example could be something like this. Okay, if I took potassium iodide and mixed it with lead 2 nitrate. Okay, if I mix these two things together, right, on the other side, what I'm going to get is potassium nitrate, and I'll tell you later how we figured this out, okay, and lead 2 iodide. Right, this reaction produces a precipitate, right, and that's the lead iodide that is bright yellow. Lead nitrate and potassium iodide are clear. Okay, they are clear solutions. When you mix them together, you immediately get a color change and a precipitate being formed, because the physical properties of lead iodide are that it is yellow and that it is insoluble. Okay, so in the reaction, we saw a color change. And the only reason we saw the color change is because one of the products has different physical properties. Okay. All right, something else we need to keep in mind here. What does the law of conservation of mass say? Right, okay? Whatever mass I start with, I have to have the same mass when I'm done. The mass of the products has to, the mass of the products has to equal the mass of the reactants. All right, that means I have to have the same number of every atom on both sides. Okay, is that true right now, the way I've written this equation? How many iodines on this side? How many over there? 2. Can I create an iodine up from nothing? Nope, I cannot. Okay, so I need to make sure that this reaction is balanced. Okay, that is, I have to put in coefficients. Okay, I can't just go, oh, well, I'll just put 2 iodines here. That's not how this works. Okay, this compound here, potassium iodide, has already been swapped and dropped. This is potassium iodide. This is a, this is a +1 and this is a -1. So someone's already dropped and swapped that. I can't just put a 2 here. But what I can say, okay, is that there are 2 molecules of that stuff on that side. Okay? I can make more of it, but I can't change what it is in order to make it balance. Right? So now, I'll get there. You're thinking ahead. That's good. I like that. Okay. So now what I've done here is I've made sure that there's 2 iodines on both sides. But as Felix pointed out, now I have 2 potassium over here, but I don't have 2 over there. Okay. Well, then I'll just go over here and do this. Okay. I'll say there's 2 potassium nitrates. Right. Now, how many nitrates do I have now? 2. How many are over here? 2. Right? So when I did that, I made the rest of it work out. Yeah. Okay? We call that balancing a reaction. It's another thing we're going to learn how to do today. The reason we do it is to make it so that a reaction isn't magically producing or destroying any matter. Okay? We have to obey those kind of immutable physical laws. All right. So first kind of reaction we're going to talk about is a synthesis reaction. Right? And in a synthesis reaction, okay, we have 2 elements combining to form a single compound. Okay. So this first one here would be an example, right? I would have 2 magnesium atoms reacting with 1 molecule of oxygen to produce 2 molecules of magnesium oxide. Okay. Do I have the same number of oxygens on both sides? Okay. I've got how many oxygen atoms here? 2. How many over here? 2. Okay. How many magnesiums? 2 and 2. All right. You can ignore the S's and the G's. It's not something we have to do in Science 10, but I kind of do it out of habit. This indicates that this is solid. Okay. So this is magnesium metal, oxygen gas. It's producing magnesium oxide, which is a solid. Okay. All right. And then this other example here, we're taking 2 potassium atoms represented by these 2 blue spheres. Okay. And we're reacting that with 1 molecule of bromine. All right, so you can see that the bromine atoms are attached. Bromine is one of those special ones that we highlighted on our periodic tables, okay, or that I changed the color for you on. Right, it's one of the ones that's diatomic. That is, it comes as a pair all the time. So those 2 elements are going to react, and they are going to form 2 molecules of potassium bromide. Okay, so here would be 1 molecule of potassium bromide, and there would be the other molecule of potassium bromide. Okay, so in a synthesis reaction, we go from 2 elements to 1 compound. Questions on synthesis? It's pretty straightforward. Okay, the opposite of synthesis. Once I've synthesized something, it could possibly break down. Okay, we call breaking down decomposition. So some molecules will decompose. Okay, that is, they will just break apart. Okay, some you have to force them apart, okay, but you can do it. Okay, in this reaction here, okay, if you run or arc an electric current through water, you can separate it into hydrogen gas and oxygen gas. Right, it's essentially the way that rocket fuel is produced. Right, they form the 2 gases and then they cool them to liquefy them, okay, and that's how they make rocket fuel. So in this reaction here, we have 2 molecules of water breaking down into hydrogen gas and oxygen gas. All right. Now, how many hydrogen atoms do I have over here? 4. Right. Okay. Because I've got 2 molecules of water, and every water molecule has 2 hydrogens in it. So this coefficient means multiply the thing behind me. Okay. So 2 times 2 is 4, and over here I got 4. Right. There's how many oxygens here? 2, right? And then over here there are 2. So this reaction is balanced. All right. Another example here is if I took nitrogen triiodide, okay, it could break down into nitrogen gas and iodine liquid. Right? And so we would see that instead. Okay. This is also, guys, where it's important to learn, not to memorize, but just to kind of be always checking on your periodic table if any element you produce is a special element. Okay, if it is, you need to write it like those ones have been written. okay, as a 2 or as a 4 or as an 8, whichever it comes as, okay, because otherwise you won't be able to balance the reaction correctly. Okay, so in simple decomposition, we're only going to have one reactant, okay, one single molecule, and it's going to break down into usually its elements, but sometimes it actually, if it's a really big molecule, it might break down into 2 smaller molecules or 3 smaller molecules, okay, depending on. Most of the time, we'll be dealing with this kind of a decomposition reaction, one compound to 2 elements. Okay. All right, questions on decomposition? Okay. All right, so on your periodic table, remember that we identified, okay, that nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine, okay, all came as 2s, as does hydrogen. Okay, so those are the ones that come as pairs. Okay, and we said that phosphorus came as a 4, okay, and sulfur as an 8. Okay, those are our special molecular elements. That is, they come as a molecule when they are an element. Okay, they bond with themselves. All right, combustion reactions are probably the trickiest of all. Okay, in a combustion reaction, you have the complete burning of a fuel of some kind in the presence of oxygen. It always forms the same products. Okay? The products of any combustion reaction are always carbon dioxide and water. Okay? So what you will see on the reactant side is usually what we call a hydrocarbon. Okay? This is a hydrocarbon because it's carbon and hydrogen together. Okay? And then it's got to be reacting with oxygen. We know things don't burn. There's no fire if there's no oxygen. Okay? Those two things react, and they will always produce carbon dioxide and water. Okay? The water may be a liquid or a vapor, depending on the type, but you're never going to have to worry about that, because you don't have to write in the states of matter in your reactions. Okay, so in this reaction here, okay, anyone know what C3H8 is? We use it a lot, actually. It's propane, yeah. Okay? It's the stuff you use in a barbecue. Right? If you have a propane barbecue, if you have a natural gas barbecue, different, but okay, it's what we use there. And it's burning, like we say, in the presence of oxygen. So let's just check and make sure that this thing is balanced, okay? There are how many carbons over here? 3, okay? How many over here? 3, okay. How many hydrogens over here? 8, okay? And 4 times 2 over here is also 8. All right, on this side, on the product side, how many oxygens are there? Thank you. Okay, so there's in carbon dioxide, in every carbon dioxide molecule there are 2, and there are 3 carbon dioxide molecules, so that gives us 6, plus how many more? 4. Okay, so we have a total of 10 oxygen atoms on the product side, and do we have 10 over here? We do. Okay, so when you're balancing a reaction, you have to make sure you're looking everywhere when you're doing that. Okay, and that's the thing that's tricky about combustion reactions, is that combustion reactions have different balancing rules than all the other reactions. Okay, when we're balancing any kind of reaction other than combustion, we just look for the biggest number and we balance it first. Generally, that'll work out. Okay, so if something is a 2, but I got something else that's a 4, I'm going to balance the 4 first. Okay, always go with the biggest. With combustion reactions, there are different rules, and you're going to need to write these balancing rules down. Okay, balance alphabetically. Carbon, then balance hydrogen, then balance oxygen. Always balance oxygen last. And rule number 2 is what we call the rule of 2. Okay? A master and an apprentice. If you're a Star Wars person, you know what that means, but that's not actually the rule. Okay? Now, the rule of 2 is this. Okay? If there's an even number of carbons, number. Okay, if there is an even number of carbon atoms, start the balancing with a 2. I'm going to show you what that looks like here in just a second. Okay, so you might want to write this example down just to illustrate as well. All right, so if I have a combustion reaction where I have an even number of carbons, okay, I will run into a problem when I try to balance. Okay, if I just follow rule number 1, which is balance alphabetically, I'm going to run into this problem. Okay, I'm going to go, okay, there's 4 carbons, so I'm going to put a 4 here, and there's 10 hydrogens, so I'm going to put a 5 here, okay, because 5 times 2 is 10, and then I'm going to have 5 oxygens here, plus another 8, which gives me 13. Okay, what times 2 is 13? 6.5. Can I have 6.5 molecules? No. Okay, that's where the problem is. Okay, I can't write a decimal in here because that indicates that I had a half of something, and Dalton said you can't do that. Even if it's a molecule, I can't have half of it, right? Then I don't have the whole thing. So what we do instead to eliminate that 0.5 problem is we start the reaction with a 2. Okay? If we put a 2 here, we're going to double everything we have. And when you double a half, you get a whole, right? So it's going to eliminate our 1/2 problem that we had a minute ago. So now there are how many carbon atoms? 8. So I go over here and I write an 8. I still balance alphabetically. Okay, 2 times 10 is 20. So I need to put what in front of this? Okay, I've got 20 hydrogens over here. How do I get 20 hydrogens here? Put a 10 here. Okay, now I got to look at my oxygens because we said balance oxygen last. Vince, you're looking at me like I'm crazy. Where did I lose you? Okay, so we got 20, and now 10 times 2 is 20, right? Okay, now over here, there are 10 oxygen atoms in this compound, and there are 16 more here. Everybody follow my math? Okay, so 10 plus 16 is 26. What times 2 is 26? 13. Okay, I've got all whole numbers, and now it's balanced. Okay, now there's the same number of oxygens and hydrogens and carbons on both sides. Now, while that may right now look a little tricky, trust me, that's going to be the easiest thing for you in about 2 days. Okay, once you do a few of these, that's going to be like the easiest part. Okay, so that's combustion reactions. Like I said, they got all the weird rules. Okay, all the other ones kind of follow the same rules. Okay, there's 2 kinds of replacement reactions. There's single replacement reactions and there's double replacement reactions. In all replacement reactions, you only have ionic compounds. Okay, there are never going to be molecular compounds in any type of replacement reaction. You can have elements in ionic compounds, you can have ionic compounds only, but you cannot have any molecular compounds. Okay, so in a single replacement reaction, what happens is an element by itself reacts with an ionic compound. Okay, what happens is one of the things in the ionic compound is replaced by this element. Okay, now copper, metal or non-metal? Metal. Okay, whatever this element is that's out here by itself is going to replace the part of the ionic compound that it is like. All right, so it's going to replace the metal, which in this case is silver. All right, so that means that silver will end up by itself and copper will end up in solution with nitrate. Okay, so there is a replacement that happens here. Right? If this was a non-metal, then it would have replaced the non-metal in the compound. Everybody follow me there? Okay. We like to, we kind of say this like it's this guy sees these two people together, but he likes her, so he like rolls this guy, tells him to take a hike and takes off with his girl, and that guy winds up alone. Yeah, it's kind of like that. All right. All right, but again, these are ionic compounds, which means you have to have a metal and a non-metal. Okay, you can't have the two metals together. All right, chemistry is very old-fashioned. Okay, there's nothing wrong with in real life the other thing, but okay, in chemistry it can't happen. Okay, in chemistry, two metals do never end up together. Okay, and two non-metals never end up together. That's just chemistry. All right, in real life, fine, no problem. But okay, in chemistry it can't happen because then you wouldn't have an ionic compound. Right, you have to have a metal and a non-metal. Okay, that's where the analogy breaks down. Breaks down fast actually, but all right. So in this reaction here, okay, like we said, we got this metal, okay, reacting with this ionic compound. What did we produce here? Silver. This is where the alchemists got their ideas from, is reactions like this. Okay, if you take this reaction, you can take like a penny or a piece of copper wire. Not that you can get a penny anymore, but okay, a piece of copper wire even, and put it in a solution of silver nitrate and leave it overnight. When you come back, okay, instead of having a clear solution with a piece of copper in it, you'll have a blue solution with silver in it. Okay, and when we used to have pennies, you could actually get the penny, it would plate out. Okay, the silver would plate out on the penny, and you'd have like a silver penny. Right? If you could scrape the silver off, it'd still be copper underneath, but you could actually like plate it out on there. Right? This is where the alchemists thought, I turned copper into silver, but they really didn't. Okay, they had silver there all along. Right? If they could have silver nitrate. Now, if you're thinking, I got to break into the chem lab and get me some silver nitrate, we don't have a lot of it, like tiny little bottle. Okay, why? Yeah, it's extremely expensive. You're not going to get ahead like economically by doing this reaction, because to buy silver nitrate is a lot of money because it contains silver. Okay, and to make this compound, they have to actually use silver in it. So, yeah, you're not going to get rich on that reaction unless you have a supply of free silver nitrate somewhere, which you don't. Okay. The other kind, the other way a single replacement reaction could go is if you had a non-metal instead of copper reacting with an ionic compound. So if we had, let's say, all right, so chlorine is one of our special elements. So when it's by itself, it's a 2. Okay, it's going to react with potassium iodide. All right, so who's it going to replace? The iodide. Okay, it has to replace what it's like. This is a non-metal, so it's got to replace the non-metal. So that means that iodine, which is also special, is going to end up by itself, and chlorine will end up in a compound with potassium. Right, now, is that reaction balanced? It's not, right? Over here, there's 2 chlorines, right? And remember, we don't follow the combustion rules. I just go with the biggest number. 2 is the biggest number, so I'll start here. There's 2 chlorines over here, and there's only 1 over here. So what do I have to do with this compound? Right, put a 2. Where do I put the 2? Yeah, right here. Okay, put it at the beginning, right? I can't do this. I can't put a 2 here. Okay, that doesn't work. All right, so now that I've done that, I have 2 chlorines on that side. I have 2 potassiums now, though. Okay, how many potassium over here? Just 1. All right, so if I put a 2 here, that makes my potassium work, and it also balances my iodine. right? Now the equation is balanced. Always a good sign. If you get to like the last thing and the number you put in makes something else work, you probably did it right. All right, questions on the single replacement? Okay, last one, double replacement. Double replacement is two ionic compounds reacting with each other. All right, so two ionic compounds reacting to form two new ionic compounds. All right, so in this one, all we do is swap the metals. Okay, we're going to make two new ionic compounds. The two metals need to have new partners on the other side. So on this side, calcium is with chlorine. Over here, calcium has to be with carbonate. Okay, it can't be with the partner it had over here. Right, it has to be with the other one. It can't end up with sodium because sodium is a metal. Right, so all we do is swap the metals so that they end up with new partners on the other side. So we got calcium chloride reacting with sodium carbonate. That's going to produce calcium carbonate and sodium chloride. Okay, is that reaction balanced? Okay, I got one calcium over here. I got one calcium over there. Okay, I've got two chlorines here and two chlorines over here, two sodiums over here, two sodiums here, okay, and one carbonate and one carbonate. So it looks like it's balanced. All right, questions on the 5 reaction types. So we got synthesis, where we got 2 elements react to form a compound. Decomposition, where one compound breaks down into its elements. Combustion, where a hydrocarbon reacts with oxygen to produce what 2 things? Oh, I think you have your notes right in front of you. You might be able to look it up. Water and carbon dioxide. Okay, always the same 2 things. No matter what's burning, okay, if it's a hydrocarbon, it's making carbon dioxide and water. Okay, then we have the 2 replacement reactions, single and double. Right, those are our 5 reaction types. Okay, and they all look considerably different. All right, when we communicate a chemical reaction, it has to be balanced. Right, we have to obey the law of conservation of mass. Okay, so there have to be equal amounts of substances on both sides, and that can get tricky. Okay, when there's a lot of rearrangement going on, because then it gets hard to track where everything goes. So in this reaction here, okay, I've got 3 nitrogen dioxide molecules reacting with 1 molecule of water. That's producing 2 molecules of hydrogen nitrate and 1 molecule of nitrogen monoxide. Right. So when I'm balancing this, okay, how many nitrogen atoms are on this side? 3. These are the only ones. Okay, and over here, okay, are there 3 on this side? There's 3. There's 2 here, plus 1 more is 3. They don't have to be together. They just have to be on that side. Okay, there's 3 on the reactant side. There's 3 on the product side. Okay, they may split up. They may go to different compounds. All I have to make sure of is that the same number on both sides of the arrow. Right, so imagine the arrow is the balance of a scale. There has to be the same number on both sides. Doesn't matter if they're together or not, as long as there's the same number on both sides. All right, on this one, on this side here, how many oxygens are there? There's 6 here, and 1 more is 7. Okay, there's 7 oxygens, 1 here and 6 here. And over here, there's 2 times 3 is 6, and 1 more is 7. All right, so it can get tricky. You always have to be looking to make sure you're catching them all. All right, so important sentence here. Okay, balanced chemical reaction is one in which the total number of each kind of atom or ion in the reaction is equal to the total number of the same kind of atom or ion in the products. Okay, we have to make sure that that is balanced. Okay, so I would like you guys to try, let's just say the first two here. Okay, here's what I want you to do with the first two. I want you to identify the type of reaction, single replacement, combustion, whatever. Okay, I want you to write it out in words, so write the names of all the compounds and elements, and then balance it. Okay, so identify the type, write it in words, and balance it. All right, give you a few minutes to try those first two. Okay, let's look at least the first one here. What kind of reaction is the first one? It's a synthesis reaction, right? We got element plus an element making a compound. All right, so our first one here is a synthesis reaction. To write it out in words, okay, this is nitrogen plus hydrogen, okay, and that's going to form nitrogen trihydride. Okay, just writing out the names of everything. Even though nitrogen and hydrogen have 2's beside them, that's how they are as an element. It doesn't change how I write their name. All right, now I need to balance this thing. So right now, okay, there are 3 hydrogens on this side, okay, and there's only 2 over here. How am I going to even that out? What's the lowest common multiple of 2 and 3? 6. Okay, so I'm going to make sure that there's 6 on both sides and see if that helps me. Okay, what do I have to multiply this side by to get 6? 2. All right, so I put a 2 there, and what do I have to multiply this by? 3. Okay, 3 times 2 is 6. All right, now this 2 gives me 2 nitrogens, and now I have 2 nitrogens over here, so now we're good. That's balanced. All right, so if you run into that problem, balancing, you're always trying to find the lowest common multiple. Okay, how many people are done the second one? All right, let's look at that one then too. What kind of reaction is that? That reaction should look really, really familiar. It's a single replacement reaction. It was the example for the single replacement reaction. Okay, copper plus silver nitrate made silver, okay, and copper nitrate. So this is single replacement. So you can always abbreviate, just SR will be fine. So we have copper, okay, reacting with silver nitrate, and that's going to produce silver and copper 2 nitrate. Okay, this is where all that naming stuff really matters. Because at some point in the near future, okay, you're going to get an assignment where you're going to have to do exactly what you're doing here. Write out a reaction in words, balance it, and identify the type. If you can't write the names, then you're going to lose marks. Right? So we have to be able to write the names, okay, of all the compounds. And you'll get some that go in reverse. The reaction will be given to you in words, and you'll have to write it in formula form and balance it. Okay? So it's really important to be able to write our chemical names and formulas. All right, to balance this thing, okay, I'm going to start with the largest number. Over here, there are 2 nitrates, right? So I'm going to go back over here and make sure that I have 2 nitrates. When I do that, that gives me 2 silvers. So I'm going to go over here and make sure that my silvers are balanced, and there's 1 copper on each side. So now my reaction works. Okay. Okay, try those 3, same thing. So what kind of reaction is the third one? It's a combustion reaction, right? We have carbon and hydrogen reacting with oxygen to produce water and carbon dioxide. So we'll just write beside that it's combustion, and then we'll write it out. So this would be carbon tetrahydride. Okay. If it gets, some of these can get beyond what we've talked about prefixes for. If that's the case, then I'll give you the name, okay? Or you can just write fuel, okay? Plus oxygen, okay? And that's going to produce water, and please just write it as water, okay? We don't need to get more complex than that, okay? Plus carbon dioxide. Okay, There's two balancing rules for combustion reactions. Do I need them both for this one? I do not. I have an odd number of carbons in that I only have one. Okay, so in balancing, I have one carbon on this side because I got to balance alphabetically. I have one carbon over here. So far, so good. Over here, I have 4 hydrogens. Over here, I only have 2. So what needs to go in front of the water? A 2. Okay, now that gives me 2 oxygens here and 2 oxygens here for a total of 4. 2 times 2 is 4, and now I've got the reaction balanced. Question? On where? Here? Because this is its element form. Yeah, remember, it's one of the special ones. So any of the special ones, this is how they are as an element. They never come as a single atom. Yeah. Okay, how many people have done this one with water? Okay, what kind of reaction is that? Simple decomposition. Okay, in fact, it was the example simple decomposition reaction. So we have water, and it's breaking down into hydrogen. Okay, so as we just said, we don't use prefixes on these. These are their element form. Okay, plus oxygen. And then we have to balance. Okay, already the hydrogens are balanced, but the oxygens are not. So when I balance them, that'll throw off my hydrogens. There's 2 oxygen over here, so I need to put a 2 here to balance the oxygens, which gives me 4 hydrogens. So I need to put a 2 here to balance my hydrogens. Okay, everybody with me on that one? All right, how many people are done this one with the chlorine? Okay, let's go over that one then too. Okay, what kind of reaction is that? Got an element reacting with an ionic compound. Single replacement. Okay, so in this single replacement reaction, we have chlorine plus sodium iodide plus sodium chloride. Sorry, whoops, not plus, makes, I skipped something there. Makes iodine plus sodium chloride, chloride. All right, so when you're writing this out, if this was on an assignment, okay, you'd get like 1 mark for having the reaction written out in words correctly, 1 mark for the reaction type, and 1 mark for having it balanced correctly. All right, so it's really important then that we get all of the names correct, because if we make 1 mistake, we just lose the mark for that part. Okay, so in balancing this, I can start with iodine or chlorine. It doesn't matter. They're both 2s. Okay, I'm going to start with the chlorine. I'm going to put a 2 here to balance the chlorines. When I do that, that's going to give me 2 sodium. So I got to go back over here and make sure I have 2 sodium. When I do that, it gives me 2 iodine, and it's done. Okay. How are we feeling about the balancing? Right? Basically, you're just hopping back and forth between products and reactants until everything is done. Right? All right, try those last 2. See how you do on those examples. Okay, so if we're looking at this one here, okay, what we have is what kind of reaction first off? Double replacement, right? Because it's 2 ionic compounds to form 2 new ionic compounds. So we will have calcium chloride reacting with sodium carbonate to form calcium carbonate and sodium chloride. Okay, and to balance this thing, I can start with chlorine or sodium. It doesn't matter. They're both a 2. Okay, I want to start with the largest number and go down from there. So I'll start with chlorine. I'm going to put a 2 here to balance the 2 chlorines on that side. When I do that, that gives me 2 sodiums, and I have 2 sodiums over here now, so that's balanced. I have 1 carbonate and 1 carbonate over here, and I have 1 calcium and 1 calcium. So all I needed to do was add that 1, 2. All right. Last one. What kind of reaction is that? It's also a double replacement reaction. And anytime you see a reaction that has no subscript numbers, smile, because it's already balanced. because everything is a what? Everything's a 1. Okay, so if there's no subscripts, you don't have any balancing to do. Okay, so when we write this one out in words, okay, we got hydrogen chloride plus potassium hydroxide and it gives us water and potassium chloride. Okay, so it should look like that. Okay, questions on how those work? Okay, it's going to take a bit of practice, but okay, once we get the hang of those, they should go pretty quick. Okay, so I want you guys to try those 5 for right now, okay? And I want you to do the same thing, okay? List the type of reaction, so same thing we did on the other ones, okay? Balance it and write it out in words, right? And then we're going to flip it and we're going to give you the reaction in words and have you write it out in formula form, identify and balance.